Hi everybody, my name is Michael Wong. I've been involved in standards for quite some time, both in C++, in OpenMP, now with Khronos, OpenCL, Sicko. So I want to talk today about where C++ is going with heterogeneous computing, specifically comparing Sicko, HPX, Cocos, and Raja. These are some of the most popular C++ heterogeneous programming styles there are. Oh, by the way, folks, if you guys want to grab some beers now, no problem. Just go ahead and start with that. So my talk is the talk today is going to give you a bit of an overview of where C++ is going in terms of heterogeneous computing. I chair SG14, which is a group that is handling adding heterogeneous computing to C++. So we have had some goals. We're going to also look at a few compatible C++ implementation out there that is already doing heterogeneous computing, meaning some of this you can download for free, some of this you might have to be involved in some national labs in order to access them. That's okay. So the popular candidates are typically Sicko, which is a Khronos standard, HPX from Louisiana State University is also here, Cocos from Sandia Lab, and Raja from Lawrence Livermore Lab. Okay, and then I want to expand a little bit on the state of C++ concurrency and parallelism, and finally talk a little bit about where C++ executor is going in terms of in 2020, and if we have time, we might also look at where SIMD vector is going. So, with the C++ standard that we have today, it's all about CPU. None of it is actually designed for GPU computing. Too bad. But what we are able to do is that we can give you great CPU latency computations using what's called the concurrency technical specification. You can get great CPU throughput computations using parallelism TS. And then finally, what we want to do is get great support for heterogeneous computing in the future. Now, there are many candidates. This is not the first time we try to design heterogeneous computing, GPU computing, into a standard. There are all these languages that have designed it, and there are actually these languages that actually have usage experience. That's one of the most important things. At the very least, these have already been used. Things like OpenMP, OpenACC, that should be HPX, Sicko, OpenCL, CUDA, all have significant usage experience. Most of these languages started out as a kind of a graphics language, and over time they've evolved into a general purpose computing language. Of course, we think at the standard level that grand unification is possible. What we have right now is almost there, but there's no coherent drive to get us to GPU computing in C++. Okay? It turns out that if we continue to work there, it would only need about 20% more, and we would be able to get there. So this is what we're going at. We're looking at something that enables massive parallel dispatch with heterogeneous computing by 2020. We're looking at an integrated approach such that C++ can marry concurrency, parallelism, and coroutines. And then we wanted to have something that works for both high-performance computing, for games, for consumers, for embedded, for FPGA. And then we also want to make asynchrony the core concept there. We want to be able to support whether it's a discrete GPU unit or whether it's an APU unit. And we want to be able to support the various new architectures like high bandwidth memory, distributed architectures. This was kind of agreed on in a meeting in February of this year in 2016 in Jacksonville. Now, there are candidates out there, and as I said before, between Sicko, NVIDIA's agency, HCC is an AMD-led initiative called Heterogeneous Computing Compiler. You can get that right now. HPX from Louisiana State University, C++M, Cocos, and Raja are some of the most popular candidates. And I want to spend some time just to pick out some of the key ones, especially of interest to the form that we're at right now, which is supercomputing, meaning that most of the people are going to be interested in what is interesting to high-performance computing. So with that, I want to talk about where Sicko stands, where HPX stands, where Cocos stands, and where Raja stands. Now, one of the interesting things I've learned, and I just attended a full discussion at Berkeley, where they talked about what are all the heterogeneous C++ alternatives. There was all of us attending, there was Sicko people attending, there was all these people attending as well too. And we kind of looked at and analyzed what each one means. So I'm not going to reproduce that all two-day discussion. Some of it is streaming online that people can get if you're from national labs. But because I've been designing languages for, I don't know, probably 20 years, and specifically heterogeneous language for the last 5-6 years, I wanted to give you my impression of what was the key takeaway I got out of these languages. Meaning, we're never, at the C++ standard level, we're never going to actually take them verbatim. We're going to take the most important learnings from each one of these and try to abstract out how to best fit that with C++ polymorphism, with C++ type safety, static compilation paradigm. But one thing I have learned out of that two-day discussion was that all these models are more similar than they differ. They were all trying to solve the same problem, and as often happens in computer science, they tend to solve the problem in similar ways, which pretty much means we're converging on a pretty close solution. So they all are exclusively C++. Let's put that aside right away. We're not talking about making it work for Fortran or C, or something, or Ada, whatever if Ada still exists. They all use, it's all about C++. And indeed, it's confirming that this is where the world is going. People use C++ for complicated computational fluid dynamics computation. They use it for artificial intelligence like TensorFlow, machine learning, machine vision. These things all use some kind of graph programming language requiring complicated tiling and convolutions. And these convolutions requires complicated graph theory that can generally be best done if you have type safety. So as a result, they all use C++ 11 lambdas as a way of dispatching a kind of a throwaway functions to get it on another thread so that they can take care of it. They all use some form of execution policy to separate concern. Now this actually is one of the most important points. Traditional languages that uses pragmas, and I don't want to name any particular candidates, they tend not to be able to separate concern. Everything is in the pragma itself. By separation of concern, I mean, what is the parallelism? Where is it? How is it expressed? Where is the resource? Okay, so most of these languages take advantage of C++ ability to give you this separation of concerns. The other thing is they all have some form of dimensional shape for the range of data. They might call it different things. They might call it set data. They might call it dim. Somehow you have to. It's clear. You have to have some way of saying what is the area of space that you want to work on in your GPU. Okay. The other final thing is they are all, oddly enough, and not surprisingly, they all aim to be integrated at some point into the C++ standard. Because one thing that we know is that national labs who do exascale computing are very early adapters of hardware, but they're very late adapters of software programming models. Okay, so they want something that is stable. They want something that can last. They don't want a research language, because you just don't know if that's going to continue. So all of them wants to live in the C++ standard, and that's completely understandable. So let's start with Sicko. Each one of these, I'm only going to give 2 pages because that's about all the time. I mean, if you want to find out more, Sicko you can download freely now. If you're in the national labs, you should be able to gain access to Cocos, Raja, HPX. You can download freely as well too. I'm sure Ahmed would love to give you that information. So Sicko, one of the big thing about Sicko, and I'm actually kind of new to Sicko. There are people here far more expert about it. Ruman's here and Peter's here. I'm glad you guys are going to be able to answer some of the in-depth questions about it. But I do have an overview that I can say. It's what's called an explicit parallelism model. It uses it queues the executions, and almost every model these days works in task and database parallelism. There are very few models that really only work in one because they realize that it has to be both. It uses OpenCL or SPIR-V to dispatch to multiple devices, and it's pretty much designed from the ground up to dispatch to most forms of accelerators. The limiting factor, I believe, is how fast the vendors themselves are able to support that translation, give you that translation device. For instance, NVIDIA isn't the fastest at giving you the latest ICV, whereas AMD and Intel and to some extent ARM, and other people are very fast at giving you the latest ICV. That translation layer is what allows you to generate code to an intermediate language, and then now you can dispatch out to whatever device that you happen to need. That's the beauty of that trick. It implements the parallelism TS, which I think Rumen's going to talk about after me. So that's good. The parallelism TS is what's ratified in the C++ 17 standard. It gives you parallel standard template library. So all the C++ standard library like sort, transform, findIf have their parallel equivalents. It supports a rich ecosystem that now supports things like Eigen, TensorFlow, neural networks, and machine vision. Now, one key thing that I always put over here is I'm always watching out what is the data movement model. In my view, having worked with the OpenMP model of accelerator, OpenACC model of accelerator, the cell processors, when I was at IBM, I used to work on a cell processor. I worked on the compiler that worked on that. The most important thing was how was data how was data movement treated? How is data being moved from the CPU to the GPU and synchronized back? That is by far the most complex problem. Sicko differs from almost all the other languages that I'm going to talk about in that it gives you an implicit data movement model using what's called dependency call graphs that enables really efficient, in my view, synchronizations and data transfer. What that means is it relieves you of having to think about explicitly moving data from CPU to GPU. Oops, there's some update here. Oh, I got to synchronize back again. Oh my God, I got the result back. Now I got to synchronize it back. That might work in fairly simple models you can think of. Over time, that's going to become very much difficult to handle. Sicko relieves you of that in that the runtime automatically, just in time, delivers the data to when you need it. Now this follows naturally that the data follows the kernel execution, in my view. It's not the only possibility though. I do recognize that at some point you do need to have explicit data movement, and I'll talk about that in a moment. But when I took notes, the most interesting contribution from Sicko, in my view, is that it separates memory storage and data access using these idea called accessors and storage buffers. It's highly developed internally using this dependency call graph. Okay. The other thing it has, which is a little subtle, is about the idea that you have multiple compilations, compilation model using a single source model. Okay. I won't necessarily go into that unless people ask me, but let me just take a look at what the code looks like. So Sicko, as you can see, is entirely C++. Okay. There's nothing new, there's no new keywords here. All of it is just additional library functions. There is the header, and then and immediately you have these buffers, which allows you to encapsulate data into Sicko buffers, which are going to be mapped or copied to or from OpenCL devices, which could be any GPU, some FPGA perhaps. Okay. The key thing is, as I said, it's a queuing model. So you have to create a queue to queue the commands through. Okay. And the other thing is, this is the part that gives you the queuing, and then this part, this CGH is a short name for call graph handler, and it submits to the queue all the work that's described in the handler using a lambda. You can see the beginning of a lambda expression here. Okay, and down here is the dependency call graph. You're telling the dependency of the buffers which way, whether you want to read it or you want to write it. Okay, and that's it. That essentially describes the data movement that would be implicitly generated using the runtime. Okay, the rest of it is just the computation itself. It's a parallel for using a three-way add of an A, B, and I. And here, by the way, is the dimension again. Okay, that I mentioned is common now. Is common across all the other designs. And this code, of course, this part of it, because it's a single source model, this code is executed on the GPU. Okay, some of this other code is executed on the CPU. That's the essence of a single source model. Okay. Let's take a look at HPX, and I want to thank people for some of these slides because these slides were presented during this major summit on heterogeneous computing C++ we had at the National Labs 2 weeks ago. So HPX is a standard library that's based closely on the C++ parallelism and the concurrency TS. C++ already has these technical specifications for parallelism, which was adapted in the 17, and concurrency, which has futures in it. What Hartmut tried to do was take all these, start implementing it, but with the mind for distributed computing. He started this because he wanted this to essentially replace MPI. It's C++ MPI, in short. That was the main key. But it turns out that distributed computing and heterogeneous computing is very similar. It all depends on whether the cores are heavyweight CPU cores or lightweight GPU cores, whatever it is. Okay, so as a result, he has already designed something that scales very well on thousands of GPU cores, thousands of CPU cores, because in the future you don't know what it is, that model that you're going for. It's an explicit parallelism model, word queuing, message-driven computation, using task-based, fork join, parallel algorithms, as well as asynchronous continuation. These cover all the different methodologies for parallelism in there. Okay. It has execution policies, as I said, for most of these models, and describes what the sequence is. And they also use something called grain size to try to make it so that it fits within a particular cache line. The data movement is explicit. Okay. Now you begin to see models where you have to explicitly tell it whether you should move the data to GPU or move it back or synchronize it. Now, it is entirely possible for them to use implicit data movement, and they've thought about it, just like we have started thinking about adding explicit data movement. The data placement uses something very natural, using HPX, what they call vectors, partition vectors, and allocator traits. Very C++-like way of doing it. Now, the most interesting contribution when I listened to that talk, and Hartman and I have talked a lot before, is that they use distributed computing nodes. They design it for distributed computing nodes, which it's a wonderful replacement for MPI with asynchronous algorithm executions. The other thing is that they also have these execution policies with par.on executors and grain size. Let me show you what that means. You see that here's a parallel algorithm that rebinds an execution policy. These dot-ons are executor objects saying where and when to execute these things. These dot-with are parameter objects that you can add, like the grain size, some parameter, maybe the cache line, maybe some cache affinity or CPU affinity. So it's a very natural way of writing C++ so that you have vector double D, parallel fill. I'm going to do a parallel fill here using a par.on policy of this exec, which I have already designed what the exec is. The exec is an executor, which has a lot of little details in it, and I'll show you what those look like that's going to emerge from C++, with par 1, par 2, begin in 0, and filling it with 0. And this will fill everything in parallel on the GPU itself. At a more complicated level, you see these dot product vectorizations, which again essentially uses very similar things. He has this data par there because this one he wants to parallelize and vectorize at the same time. Data par is actually the word that C++ standard is going to use. And further down, he uses two lambdas, okay, for this actual dot product itself. Okay, so I'm going to need a beer soon, so anyway. Let's take a look at Cocos. Thanks to Carter Edwards and Christian Trott who gave the talk there. It implements Cocos is a language that's developed mostly at Sandia National Lab for C++, very heavy C++. And one of the key things is he implements parallel patterns. He wants his names to be distinctly clear that there's a parallel pattern here, not just some three, four loops that's nested and maybe parallel, maybe not. He wants to call those things explicitly parallel for loops, so that you can identify things. Now that's a minor enhancement, but other things that are tremendous, I think, is he has execution policies, just like all the other languages I've talked about. He has execution space where the computation is. In Hartmut's language, that's called par.on. Okay, but more importantly, I think his most important contribution is the idea of this memory space and layout space. In C++, in traditional computational fluid dynamics, those two aspects give you either performance or no performance. Whether you have arrays of structures or structures of arrays are very important in this domain. Okay, so I've already mentioned the name stands out to identify the parallel pattern. He manages the inter-thread synchronizations and reductions of thread local temporaries. He has atomic views and floating point view. This is another important contribution in my mind. The fact that he has views that enable you to take beyond the rigid C++ way, where the atomics can only be on integers and integral types and pointer types and Boolean types. He now allows you to have atomics that are on floating point types. And he has views on these atomics where if it doesn't work, for instance, this atomic, let's say it's some weird 568-bit atomic, floating point atomic, which can't exist. the view means it will serialize the whole thing, so that you still maintain the atomicity of it. Okay. Apparently he has stuff like that. I don't know. I've never seen it, but anyway, that's what you have. It's definitely explicit data movement. Nobody else does, other than C++, AMP, and Sicko, do implicit data movement, because they don't build the dependency graph and access the dependency graph in the way that we do. They have memory space control and layout space control. I think those two are some of the most important contributions from Cocos, in that the memory space tells where the user data resides, whether it's in some host, some GPU, or some HBM. I haven't quite seen it develop to this extent yet, which is why I think it's positive. The other one is the layout space, whether it's going to be row or column major, whether it's going to be AOS or SOA. Okay, just to take a look at Cocos code, you'll see that there's a standard parallel for loop, but he uses pattern. He calls it parallel for with some policy n in the body, and here's a standard kind of a sparse matrix vector multiply. You'll see that he has the pattern, some team policy, and usually some n row, which gives you a description of the dimension. Okay, he also has more interesting stuff that gives you a team policy or team thread range, which enables you to do further optimizations at a more fine-grained level. These are important aspects, I think, that Cocos can contribute. There are other things too, but much of Cocos is the fact that you can now identify the layout space as well as the memory space that enables you to get the best optimizations. Okay, Raja, thanks to slides from Lawrence Livermore's David Beckinsale, talks a lot more. It's also similar in many ways. It has execution policies that enables you to in their view, their policy goes to either CUDA or OpenMP or sequential. Okay. They also have these things called index set spacings that partitions index space into segments that cover the space. And then the segments is a container of iterators that can be executed in either parallel or sequential or some dependent relationship, for instance. Okay. They tend to focus a lot more on executing loop iterations. They can handle hardware and software programming detail models, and this is part of their strength. It's an implicit data movement model, but they do handle with some extensions called Chai, gives you data movement abstraction layers. The way they do all these additions is they use abstraction layers on top of it. I think their most interesting contribution is the execution policy and these index sets and segments idea, where they can gain their parallelism in there. So here's a one where you have execution policies that control loop scheduling and execution, some reduction with a reduced policy. They actually put that in the policy itself. Okay. And don't forget, these index sets can have elements that can operate in parallel or sequential or some dependency relationship that they can describe. Okay. That's where the similarity with Sicko comes in. The dependency relationship in our case is described by the user using buffers. Okay. So you can implement a for n as just a Raja extension for nested loops. You would have the abstracts for a n nested loop, then followed by some execution policy for each index loop interchange. And then you have an index type, in this case ordered, some index set for each index ordered, and then you would have some view abstract index calculation to provide the type safety itself. The loop body would have type safety indexes. So by and large, I think Raja is very similar in that way. So those are the only four I wanted to showcase, but now I just want to step back for a moment and just tell you where C++ is going, because I just finished going to the C++ standard meeting in Issaquah last week. C++ 17 is out, okay, and we're going to have parallel algorithms in there, the red stuff, as well as progress guarantees. You have to have progress guarantees to be able to do parallel algorithms. Parallelism, the technical specification is also going to have things like library vector types and vector loop algorithms, as well as some sort of task-based parallelism. But what's interesting is that in concurrency we have TS1, which has the Microsoft continuations, the future patterns, as well as latches and barriers and atomic smart pointers. We also have TS2 coming, which is going to have these atomic views and floating point atomics. They come from Cocos. Okay, that's one of you already begin to see things that are beginning to drive into the standard, and part of that is because of the fact that all of us are attending the C++ standard meeting. Other things are going to be like lock-free programming, synchronics, and counters and queues. But executors is now on its own as a TS as well too, and I'm going to show you what that looks like. Other TSs that are relevant are things like coroutines, transactional memory. Okay. Yeah, question about that.
The parallel algorithm is without a TS, it's in the plain standard, or?
Okay, the question is the parallel algorithm part of a TS or is it part of the standard? The answer is both. It started life as part of a TS, and now it's been transferred completely into the standard, minus a few things that got dropped at the last moment. Oh, okay. And because that's what happens. The TS gives you initial reference knowledge, and then later on, once you approve, you move it into the standard. I'll tell you what's been dropped. There's no more dynamic execution policy, meaning you can't set it to a variable and use that variable later on in your parallel algorithm. Okay. The reason they didn't want that was because they didn't want to keep state. And the reason they didn't want to keep state is because they later on want to add policies, and they don't know what those policies look like. Some of them will be GPU policies, and if you keep state, these things are not going to match up well. The other thing they changed was the name. Instead of par-vec for parallel vectorized, it's now called par-unsequenced. Okay? Things are going to execute in a parallel unsequenced order. That's why they call it that. The third thing they changed is they took away the exception list, which gives you the ability to report exceptions using a list of exception pointers, and now just unwind and terminate. Oh, sorry, it doesn't unwind at all. It just terminates. Okay, and the reason for that was so that it makes it easy for you, so you don't see thousands of exception lists. Okay, later on we're going to change it so that we can allow you to add more different types of exception lists. I hope Ruben's going to talk about it, so I don't want to steal his thunder. Okay, where was I? Okay, so I want to just go over how executors look. Executors is a linchpin to allow us to get to heterogeneous computing. So C++ executors, they're kind of like they're to function execution what allocators are to memory allocation. Another way I think about it, they're like the iterators between algorithms and containers. They marry two things together. So it's been described in this paper, which we've co-authored. Now, if you think about all the different diverse control constructs that exist in the world, whether it's in C++, these happen to be in C++, well, some of them are anyway. You have for each loops, you might have parallel loops, you might have asynchronous loops, you might have task blocks, okay? Some favorite control structure, but you have all these resources that you want to run them on. They might be a thread pool, they might be an OpenMP runtime, they might be some fiber or some GPU runtime. The question is, if you don't have something that unifies these end-to-end, you're going to end up getting an end-to-end relationship. Every async is going to have to be able to access any of these resources. That's not a desirable position to have. And so there were a couple of proposals that's been going around. And thanks to these people, I want to specifically thank them for reviewing and working hard on this proposal. These slides are by Jared Hoberock. Basically what happens is we have this minimal proposal that gives you the ability to say an instruction stream is the function that you want to execute, and an executor is an interface that describes where and when to run an instruction stream. An executor might have one or more of these execute functions, and then an execute function would execute an instruction stream on lightweight execution agents. Now, going to the top part, you'll see that you might have an execution platform that might be a Linux x86, or you might have an execution resource that's the hardware abstraction. In this case, it could be a thread pool. That's just a hardware abstraction, of which you would have some execution resource, execution platform. Then you would have these execution context that manages both the bottom half here, and also manages the top part during an execution. Given this idea, you can now have these further bifurcations where they have these one-way or two-way. I'll go over that a little bit more closely. But I wanted to show you what an executor looks like. An executor looks like this. This is a simple executor. I have an execution category, which I'm going to say whether it's going to be in parallel or concurrently parallel, okay, or weakly parallel. We'll talk about that. Then I have a shape type, which gives you a tuple in this case. This is a dimension analysis part. Then these things return a future because they would manage the data and they would share and advertise the semantics of it. And then they would mediate the dependency by issuing these bulk async execute, given all these factors to, in this particular case, this bulk async execute will enable it to be dispatched to thousands, millions of threads on a GPU. Okay? So what's the big reason of executors? I've already said, and a lot of these other language design has already encapsulated the where and where do you execute it, how do you execute it. So you have placement. By default right now is at the discretion of the system in C++. You just put paw, you don't know where it's going. By default, C++ only recognizes CPUs. If the programmer wants to control the placement, you've already seen this one. This is drawn from HPX, where we say, do this in parallel on this exec1 executor, where I made some choice here. Okay? The second reason for executor is that it controls relationships with the calling thread. Okay? Right now, C++ already have these things called async launch flags. Then it's a natural place to put the executor for the async now. Okay? Now, third reason for executors is it gives you a uniform interface for scheduling semantics across control structures. You might have for each, that should be par, I forgot to put the AR. So you could say for each parallel on some executor, or async on an executor, controlling the relationships, or you might have a future then executor, or you might have a dispatch on an executor. Dispatch would be particularly useful on something that's a low latency machine for instance, for high frequency trading. So one of our goals for designing this was that it would have to work into all the C++17 and technical specification places. Okay, so this is essentially it. These are what executors look like. I'm going to close because I don't want to drag on too long because I'm probably running over. I'm going to give you a simple thread pool executor. Okay, this is a simple thread pool executor, and you can say in the context, this is my thread pool. The executor is just an embedded, okay, just an embedded struct or class. This is the my thread pool executor of T, and then it would have a execute function that submits a task to the thread pool itself, and this executor is going to be created by the context. Okay, remember the diagram relationship I had before? And that's really it. There are really only a few things. They have execution category that tells you whether they're going to run in sequential mode, vector parallel mode, or parallel concurrent mode. They have a shape type that gives you the indexing. This is all the commonalities we're drawing from all these other 4 languages up there. They generally return some kind of a future or path to some result. Okay? And by separation, these are basically all there is. You have single agent tasks that are sync execute that returns a result, async execute for asynchronous execution that returns a future result, and then execute if you want to chain the return results, okay, using a continuation pattern. There are also these multi-agent dispatch suitable for GPU executions. Okay, you might have bulk sync execute or bulk async execute and bulk then execute. Okay, and I think that's about it. I really want to stop here just to show you that all the features, all the different ways of doing executions are there. There are these post varieties, which is great for fire and forget varieties. They all have they're either non-blocking one way or non-blocking two way. For instance, for Sicko, it's pretty important for us that it's a non-blocking one way in some ways. But we also want to make sure that it can potentially block using customization points. Okay, so that's it. I'm going to stop here because I've been talking long enough. You guys have been a great audience.